d of z over d of t equals 1, d of x over d of t equals 3, dy over d of t, and the same when x equals 4, y equals 3, was 5, d of x over d of t. Question.
Question mark. Enter, enter. So we have a rectangle, so we know we have a right triangle. When given a right triangle, what theorem do you think of?
A squared plus b
A squared,
C
good.
equals c
So we have, in this case, I'm going to use the variables given. X squared plus y squared is equal to z squared. Let's go ahead and derive this piece. So we have 2x times dx over dy. And then we have, did I say dy when it's dt? What a sad day. So we have dx over dt. Go ahead and derive the rest of them while I'm deleting my mistake. Oh, that's good enough. Will the derivative of the rest look similar? Plus 2y dy over dt. And then we have 2z dz over dt. Now they gave us some measurements, didn't they? X equals how many? 4. Y equals how many? 3. Do I have a triple to find the z? Must be 5. If all fails, use Pythagorean theorem and we'll get the same thing. Okay. And then from here, let's go ahead and plug in what I know. Do I know dx over dt?
Yes, equals 3 dy over dt.
So here I have, in this case, it's going to be, oh, let's go ahead and cancel all the 2's. Since I have 2's all the way across, we like to have our smaller number. So I'm going to rewrite what I have. I have x dx over dt plus y dy over dt. You can leave a 2 if you want, but I'm going to make it easier. So we know our x is 4. Let's plug it in. And we're looking for dx over dt, so that's going to be the variable that's going to be unknown at the moment. And then I have my y is how many? 3. Now let's go ahead and reiterate what's happening here. If I want to solve for dy over dt on this one right here, wouldn't that be 1/3 of dx over dt? Let's write that out on the side. dy over dt is equal to 1/3 of dx over dt. And the nice thing about this 1/3 is that 3 is going to cancel each other out. Oh, that's a t again. I wrote x again over here. Silly day. Voila. There's our t. And we know our value of z is 5. And do I know what dz over dt is? Didn't they give it to us? 1. So if I were to further solve for this one, can I combine like terms over here?
Yeah.
Because that's technically 1, correct? So when I combine the x's, we get 5 dx over dt is equal to 5 times 1 is 5. And when I divide it by 5 on both sides, we should get b. Okay, let's go on to number 14. Whoever chose 14 is this is a really good question. Evan, let's read.
Let f be a function such that each point x, y in the graph f. The slope is given by dy over dx equals y squared minus x. The graph of f passes through the point 1, 2 and is concated down an interval 1 less than x less than 1.5. Let k be the approximation for f of 1.2 found by using the locally linear approximation of f at x equals 1. Which of the following statements about k is true?
So we need to find the equation of a tangent line. To find the equation of a tangent line, we need a point. So let's write out point. And we also need a slope. Now for this one, the point that they gave us was 5 or 1.2. Should I use, no, let's just start with this one, 1. And then we have our 2, because we're comparing something in a little bit. And our slope equation is given right here. So when I plug it in, we get 2 squared minus 1. How many would that give us? 3. So we could write our point slope formula, right? But I want to write it in a way where y is by itself. So we have our slope as 3. X times x1 is x minus 1. And I know we won't normally say y minus y1, but when I move the 2 over, we should get plus 2. Now from there, we're doing an approximation. So let's see what is happening right here. It says when I have f of 1.2, and let's plug it in, 3 times 1.2 minus 1 plus 2. Doing our tedious math here, we're going to get, that's going to be 0.2, so 0.6 plus 2, which is 2.6. What is actually happening is the following. This is concaving down, correct? So here's the actual function. In my tangent line, it's going to go through any point you want. You can put it on the top, the bottom, or the right. I would not do the top because our slope becomes 0 then. So let's say I have a point right here. And that point is at 1, 2, 1.2, 2.6. But on the actual graph, isn't that lower? So our approximation is this one, and this is actual. So let's write out. This is approximation. This is the actual as an equivalent to. So we know our approximation is under or over?
Over.
Over? There's 2 over though. Which one am I going to pick?
C.
The one that's got 1.2 and 2.6, which is C. All right, let's go on to 19. 19 is all about the definition, and I'm gonna bring my flashcard that we talked about on mean value theorem. So this one is asking us to find which part is true or false. What does it say? Which of the following must be false? So I'm going to pick one and prove to you why that's going to be false. Okay. Let's go ahead and circle D. And I'm going to define mean value theorem. And in case you're thinking, what does a card look like? To apply mean value theorem, it must be continuous and differentiable. So looking at this, condition 1, it must be continuous on the interval 0 to pi inclusive, and also it must be differentiable on the interval 0 to pi. And thinking about differentiability, y'all remember setting something equal to 0 on the denominator, also under the radical? Okay. Under the radical, this number right here cannot equal 0. So how can I manipulate? So sine of pi will be 1, because 1 minus 1 is 0. Right? So I'm going to say, if I have square root of 1 minus 1, will that cause that inside to become 0?
Yeah.
So if I were to look at our unit circle, on the very top at pi over 2, sine is at, or the order pair is 0, 1. So we know our sine is 1. When sine is 1, 1 squared is still 1. 1 minus 1 is 0. So we know it is not differentiable at this point. So therefore, we cannot use mean value theorem. That's a little more in depth.